All right, geometry students, here we are for the start of chapter 12, 12.1 tangent lines. Chapter 12 is all about circles, so we want to talk about tangent lines to start. Cross out the word that does not apply to circles. Which one of these words here is not a vocabulary word that applies to circles? That would be equilateral. Circle the word for the segment with one endpoint at the center of the circle and the other endpoint is on the circle. We call that the radius. All right. Tangent. Tangent is to a circle is a line, ray, or segment in a plane of a circle that intersects the circle at exactly one point. So this point B, all right, this point B right here, that is called the point of tangency. All right, that line AB touches the circle at one point, and it only touches at one point only. All right, if I would zoom in on that, it would touch it once. Okay, if I would zoom in even closer, if it crosses twice like this, all right, then that is not a tangent, all right, because it is touching the circle at 2 points. All right, at this point here, call that P and we'll call that Q. So there it touches at 2 points. That's not a tangent. A tangent can only touch at 1 point, okay? And like I said, it's called a point of tangency. All right, so the line can be a tangent, the segment can be a tangent, or even a ray can be a tangent. Other uses is in a right triangle, the tangent is the ratio of the side opposite an acute angle to the side adjacent. So opposite over adjacent is what tangent is. Um, Complete each statement with always, sometimes, or never. A diameter is blank to a tangent. All right? A diameter is blank a tangent. What's never a tangent? A diameter will always go through the circle once, twice. So a diameter will never do it. Okay? A tangent and a circle, sometimes, always, never, have exactly 1 point in common. All right? They always have 1 point. That's the definition. They always have 1 point in common. A radius can sometimes, always, or never be drawn to the point of tangency. It can always be drawn. All right? We'll see that today, but what that means, all right, is that if I have a circle, all right, and a tangent drawn, so I have this tangent line drawn, if I take the center of the circle, I can draw a radius to that point of tangency. All right. A tangent, sometimes, always, or never, passes through the center of a circle. It never will. Right. It never goes through a circle. It only touches on the outside. All right. Or it touches the circumference at one point. A tangent is sometimes, always, never a ray. Sometimes it's a ray. All right. As we defined above, it can be a line segment or a ray. Okay, theorem 12.1, 12.2, and 12.3. Let's talk about these. So theorem 12.1 says, if a line is tangent to a circle, then the line is perpendicular to the radius at a point of tangency. All right, so if a line is a tangent circle, then the line is perpendicular to the radius at the point of tangency. So that example I just made, this would be a right angle right there. All right, that's going to happen. Okay, as you can see right here, there's a right angle right there. Theorem 12.2, if a line in a plane of a circle is perpendicular to the radius, it is an endpoint to the radius at its endpoint on a circle, then the line is a tangent. So that's kind of like the converse. Okay, if I know I have a right angle and I'm at that point on the circle, then I know I have to be dealing with a tangent line. All right, and then 12.3 says, if two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. Okay, so if I look at this figure, this point B, I draw a tangent on this side, so there's our point of tangency, and draw a tangent on this side to C, there's a point of tangency, then that means that segment AB is going to be congruent to segment BC. All right? Those segments are going to be congruent, the same distance away from the circle. Okay? All right, so let's fill in problem 4, 5, and 6 here. So 12.1, if the line DF is tangent to circle O at K, then what pieces are going to be perpendicular? That's going to be segment DK is going to be perpendicular, should be DF. All right, I read that wrong. Segment DF is going to be perpendicular to segment OK, or line DF, perpendicular segment OK. All right, theorem 12.2. Theorem 12.2 says if line DF is perpendicular to segment OK, then that means that the line DF must be tangent to circle O. Okay? And we kind of already answered this last one. If segment BA and segment BC are tangent to circle O, then that means that segment BA and segment BC are congruent to each other. All right, finding angle measures. Segment ED is tangent to circle O. What is the value of X? What is the value of X? So circle the word that best describes the segment OD. What kind of segment is OD? Well, that's a radius, right? That's a radius. So segment OD is from there to there, right? Okay, what is the relationship? What relationship does theorem 12.1 support? Right. So what that means is that I'm going to have a right angle right there. All right. So that means that I have perpendicular. Segment OD and segment ED are perpendicular. Circle the most accurate description of the triangle. All right. Well, we know it's going to be a right triangle. Okay. So this triangle here is a right triangle. So we can use properties of right triangles to help us solve. Circle the theorem we use to solve for X. I'm going to use the triangle angle sum theorem. Right. Don't I know the measure of the three angles have to add to 180? Absolutely. So the sum of the measures is going to be 180. So that means that 38 plus the measure of angle D, which we now know as 90, plus the measure of angle E, which is X. Okay? So we'll go ahead and solve for those. So let's add those up. So I'm going to get 180 is equal to 128 plus X. We'll subtract 128 from both sides, and that's going to give me 52. Equal to X. So that angle is going to be 52 degrees. Okay? All right, go ahead and pause the video and try this one on your own. Okay, so here I have two radii and I have two tangents. All right, so I have these two are congruent to each other, and then since I have tangents, those two are congruent to each other. So actually, what kind of figure is that quadrilateral right there? That's a kite, isn't it? All right, that is a kite. Okay, so I know I have right angles right there and right there because this is a tangent. Excuse me, that's a radius and this is a tangent. That's a radius and this is a tangent. So I know they have to form right angles. Now, this is a quadrilateral. We know in a quadrilateral that the angles have to add up to 360. So that means that 90 plus 90 plus 117 plus X has to equal 360, right? Okay, so let's go ahead and solve for that. So 180 plus 117 is going to give us 297 plus X equals 360, all right? And then we'll subtract that from 360, and we're going to get X is equal to 63, all right? So 63 is our answer, so B will work, okay? All right, number 2, finding distance. What is the distance to the horizon that a person can see on a clear day from an airplane 2 miles above the Earth? Earth radius is about 4,000 miles. Okay, so the diagram to the right, the airplane is at point A and the horizon at point H. Use the information in the problem to label the distance. All right, label the distances. Okay, so when we're in the airplane, obviously we can't see forever. All right, when we look at the horizon, we see a long way when you look out the window of an airplane. All right, but you can't see forever. You can only see until the tip of the horizon there. Okay, there used to be planes in the 80s and 90s used to fly called the Concorde, and the Concorde used to gain enough altitude where you could see the curvature of the Earth. All right, they discontinued flights of those after there were a few accidents and common mechanical problems. They discontinued those, I believe, in the late 90s. All right, but in normal planes, we don't see the curvature anymore. All right, okay, so let's just fill in what we know. So here we have this triangle. In this triangle, I know that's a right angle. All right, I know the radius of the Earth, that's about 4,000 miles. So this is also 4,000 miles here. And then I know that my plane is going to be 2 miles above the Earth. Okay, so obviously it's not drawn completely to scale. This length right here is 2. All right, so what I want to do is I want to know what the distance to the horizon that I can find. So I want to find the length of AH. So in this triangle, I'm looking for that side right there. Well, it's a right triangle. I know two of the three sides, so I can use the Pythagorean theorem. All right, so let's fill in. What do we know? We know that OH is perpendicular to AH, right? So if I use the Pythagorean theorem, I'm going to have OH squared plus AH squared is equal to OA squared, okay? So that's the Pythagorean theorem. Let's plug in what we know. So if I look at this triangle, all right, I have this side is my unknown, this side is 4,000, and then the hypotenuse is 4,002. All right, so I'm going to use this right triangle right here and solve for that missing leg. Okay, so we'll have 4,000 squared plus AH squared is equal to 4,002 squared. All right, so let's write that out and see what we get. So 4,000 squared is going to give me 16 million plus AH squared is equal to 16 million, 16,004. All right, so then I'm going to subtract this over this 16 million over to this side away from this 16 million. That's going to give me 16,004. All right, square root both sides, so I'm going to get the square root of 16,004. All right, that's not perfect, so it comes out to be about 126.5069168. All right, so let's go ahead and round that. So first you can see about 127 miles of the horizon from the airplane, 2 miles above the Earth. All right, so when you look out the window of this particular airplane, you can see 127 miles to the horizon. All right, go ahead and pause the video and try this one here on your own. Similar strategy to what you just did. Go for it. All right, let's look at this triangle that we have here. Here we have this right triangle. So that right triangle that I have, all right, I have this side is 6,400. I have this side is 6,400.45. All right, and this is my unknown. So I'm going to use the Pythagorean theorem to solve for that. So I'm going to have x squared plus 6,400 squared is equal to 6,400.45 squared, right? Okay, so I'm going to subtract the 6,400 squared from both sides. So x squared is going to be equal to 6,400.45 squared minus 6,400 squared. And I have worked those out because those numbers are going to be pretty darn big. All right. So now I'm going to take the square root to get x completely by itself. All right. So there's my answer for x right there. So I'm just going to plug that, all right, into Desmos. Okay. All right. So you can't see that right now, but you can see what I'm getting here. So I'm going to do the square root of 6,400 squared, 6,400.25, excuse me, 0.45 squared minus 6,400 squared. Close off those parentheses. And I'm going to get about 76. All right, so I can see about 76 kilometers. Okay, at the top of this tower here in Toronto. Okay. All right. What is the radius of circle O? All right, so let's find the radius of the circle. So here, notice that in this triangle, the same idea, but this triangle here is the radius is unknown. Okay, so I want to use the Pythagorean theorem again, but I'm going to have to set up some algebraic stuff in order to do it. Okay, write an algebraic and numerical expression for each side of the triangle. Okay, so this side right here, that's obviously going to be x. The other leg is 10. All right, and then what is this side, the hypotenuse? Well, if I do part plus part equals whole, that's x from there to there, and then it's 6 from there to there. So altogether, that's going to be x plus 6, part plus part. Okay? So circle the longest side. Well, we know that's got to be the longest side because that's our hypotenuse. All right. So if I put this into the Pythagorean theorem, I'm going to get x squared plus 10 squared equals x plus 6 squared. All right, so let's go ahead and solve that. So I'll get x squared plus 100 is equal to, now what do I do with that? That turns into x plus 6 times x plus 6, right? Isn't that what squared means? Just do the same thing twice? Yeah, that turns into a FOIL problem, right? So let's go ahead and FOIL that. So x squared plus 100 is equal to my first term. So FOIL, first, outer, inner, last. My product of the first terms, x times x, that's x squared. My outer terms, x times 6, that's a positive 6x. My inner term, 6 times x, which is a positive 6x. And my last term, 6 times 6, is a positive 36. All right, so let's combine our like terms. So now I have x squared plus 100 is equal to x squared plus 12x plus 36. Okay? All right, so algebraically, what can happen? Well, algebraically, the x squareds can cancel out, right? Those are gone. So I'm left with 100 is equal to 12x plus 36, right? So let's just get x by itself. All right, we'll get x by itself by subtracting 36. Subtract 36, and I'll get 64 is equal to 12x. All right, then we'll get x by itself by dividing by 12. 64 divided by 12 comes up to 5.3 repeating, or 5 1/3 is equal to x. All right, so 5 1/3 is the radius of that circle. Okay? All right. Okay, problem number 4, identify a tangent. Is segment ML tangent to circle O. So again, we're using the idea that this angle right there has to be right in order for it to be a tangent, because the radius to this point of tangency, which would be potentially be L, right? And then this, our potential tangent, those have to form a right angle where they intersect. Do they? Well, all we have to do is look at this triangle. Is that triangle a right triangle? Is that a right triangle or not? And the answer is yes. All right. Yes, it is. All right. How do I know? Because 7, 24, 25, all right, is a triple. All right. Or if you forgot your triples, do 7 squared plus 24 squared. Does that equal 25 squared? All right. And if it does, which it does, all right, then I know I'm dealing with a right triangle, which means I must have this right angle right here. And if I have a right angle, that means that point is the point of tangency, which means that this segment is a tangent. All right. So that makes the segment ML a tangent segment. Okay. All right. Go ahead and pause the video and try guided number 4 here on your own. Okay, it says use the diagram in problem 4. So I'm going to use the same diagram, all right? And we're going to change some numbers here. So it says NL is 4. So that's a 4. ML is 7. And NM is 8. All right? So here's the question. Is segment ML a tangent? Is this right here, is that a right angle? Okay, well, is 4, 7, 8 one of the triples I asked you to memorize? No, it's not. But let's also use the converse of the Pythagorean theorem. Let's do 4 squared plus 7 squared. Does that equal 8 squared? All right, so I get 16 plus 49 is equal to 64. And that's going to give me 65 is equal to 64. Well, that's not a right triangle. It didn't come out to be equal. So they're not equal. In fact, what kind of triangle is it? Anybody remember how to do that part? All right, remember we put the mouth right here and we've got our shark eating, all right, this number where the A is. So this is actually an acute triangle. So that means that this triangle that we have up here is an acute triangle. So that angle is not a right angle, which means that that point cannot be a point of tangency, which means this segment cannot be a tangent segment. All right? So we just have to prove that we have a right angle right there, and we showed that we did not. Okay? All right. Go ahead and pause the video and try this one on your own. All right, so we already have a right angle right here. So we have this right triangle. All right, so let's set up the Pythagorean theorem. So I'm going to have one of the legs, which is x squared, plus the other leg, which is 12 squared, is equal to the sum of the pieces of this hypotenuse, right? So that'll be equal to x plus 8 squared. So that's going to give me x squared plus 144 is equal to x plus 8 times x plus 8, right? Okay, so let's go ahead and FOIL this over here. Remember, FOIL first, outer, inner, last. Okay, so we'll FOIL x times x. That's x squared. My outer terms is a positive 8. My inner terms is also a positive 8x. And then the last term in each set of parentheses is 8 times 8, which gives me 64. All right, so I get x squared plus 144 is equal to x squared plus 8x plus 8x plus 64. All right, now what can cancel out on both sides? The x squared, right? So I get 144 is equal to, I'm going to combine these and get 16x plus 64. All right, so I'm going to subtract 64 to both sides, right? Okay, so 144 minus 64 will give us 80 is equal to 16x. Then I'm going to divide by 16 on both sides. All right, so 80 divided by 16 is going to give me 5. All right, so that means that the radius of this circle here is 5. All right, what would the length of the hypotenuse be? Look how it checks out. What's 5 plus 8? Part plus part, 13, right? Doesn't that show a 5, 12, 13 right triangle family? You know that one, that's one of your triples. So it all works out. Okay? All right. In the figure at the right, the sides of a triangle are tangent to a circle. The circle is inscribed in the triangle. The triangle is circumscribed about the circle. So we talked about that when we talked about a circumcenter. Okay? We talked about an in-center. When we talked about those special points of concurrency in triangles a few chapters ago. Circle is inscribed in polygon. Circle O is inscribed in triangle PQR. What is the perimeter, which has a perimeter of 88 centimeters? What is the length of QY? Okay, so we can use theorem 12.3 to show that we have tangents that are congruent. Okay, so that means from P to X is the same length as P to Z. So that's going to be 15. All right? We know the distance from R to Z is 17. So from R to Y is also 17. That means that from Q to X, all right, and Q to Y, those are the same distance. Those are the same distance. So what I can do is set up a algebraic equation to solve for those. So let's give them a variable. Let's call them little x. So we know that for the perimeter of the triangle, it's going to be x plus 17 plus 17 plus 15 plus 15. Right? That's how we find perimeter. We add them all up, right? So if we add all those up, that's what we're going to get. Okay? All right, so let's fill in here. So we know that PX is congruent to PZ. We already said that. We know RZ is congruent to RY. We know QX is congruent to QY. And so that means that they're also equal. So PX equals PZ. RZ is equal to RY. And QX is equal to QY. All right, we've already mentioned that. We've already talked about it. So my perimeter is going to be the sum of all the sides. So it's going to be px plus xq plus qy plus yr plus z plus rz plus zp. All right? So if we add all those up, I know my perimeter, which is given to me as 88, is going to be equal to 15 plus 15 plus 17 plus 17 plus x plus x. Right? Those are my 6 pieces of that triangle. All right? So that's going to be 88 plus, or equals, excuse me, 88 is equal to 30 plus 34, when I add those up, plus 2x, right? Okay, so 88 is going to be equal to 64 plus 2x. I'll subtract 64 from both sides, and that's going to give me 24 is equal to 2x. So then I'll divide by 2 on each side, divide by 2, and I get 12 is equal to x. All right? So that means that this piece is 12 and this piece is 12. All right, because we know they have to be the same. Okay, awesome. All right, go ahead and pause the video and try this one on your own. Okay, not quite the same as the previous one because here we're trying to find the perimeter. All right, well, we know that the length of segment AD and the length of segment AF have to be the same. So if AD is 10, then AF is 10. We know the length of segment CF and the length of segment CE have to be the same. So if CF is 8, then CE is 8. And we also know the length of BD and BE have to be the same. So if one's 15, so is the other. So that means if I do my perimeter to add those up, my perimeter is going to be equal to 2 10s plus 2 15s plus 2 8s, right? So that's going to be 20 plus 30 plus 16. So that'll be 50 plus 16, which will give us 66 centimeters for our perimeter. Okay? All right. Excellent. Okay, go ahead and pause the video and do the lesson check. A classmate insists that segment DF is tangent to circle E. Explain how you show that your classmate is wrong. Underline the correct word or number to complete the sentence. A tangent to a circle is perpendicular to the radius. If segment DF is tangent to circle E at point F, then the measure of angle EFD has to be 90. A triangle is going to have at most one right angle. So explain why your classmate is wrong. All right? Well, angle F cannot be a right angle. All right? Because angle E already is. Right? So I have this 7, 24, 25. I have a right triangle here, but the issue is that it's kind of upside down. Right? The triangle I should have should look like this, where the right angle would be at F, not with the right angle at E. Okay, so that's the issue. Okay? All right. So a circle, all right, how do we define a circle? A circle is defined as given a point in a plane, every other point that is equidistant from that given point. And that distance is called the radius. So all of these are radii. All right, so all those distances being the same, that's going to, from this point here in the center of the radius, that is going to be our radius. Okay? Tangent to a circle. Tangent means touch. All right? Tangent means touch, not intersect. All right? It means touch. So just touching it at one point. Okay? So if I have a circle, I'm going to have a tangent that's just going to touch it at one point. That's it. Okay? And then a point of tangency, that point of tangency where they touch, that's it right there. That's our point of tangency. Okay? All right. Put a dot in the line how well you understood section 12.1, and you're now all set to do the homework. So go ahead and do that, and I will see you next time.